Log on, tune in, find out. Another good idea from Cambridge.
To this seminar, and I'm sorry to make you confused about the first word. And this is a new developed some techniques to carry out a numeric simulation for Boltzmann-BGK equation, and this is the joint work with my PhD students, and this one is a boy, and this one is a girl. Yeah, so this is the outline of the talk, and I will have some historical review, and mainly to make clear what is the word NRxx stands for, and then I will play the game to make the numerical approach for this moment method, and then the regularization of the moment system, and at last some numerical results. And so this is the Boltzmann equation, and yeah, it's showing that this is the classical Boltzmann equation. And Roger Alexander yesterday had discussed a lot of good properties of this correlation operator, but to carry out a numerical simulation for this equation, and the only problem is that this f, and it's dependent on the time t, the spatial coordinate x, and the velocity outlet c. And so for d is equal to 3, and this problem is in 7-dimensional, so we can't carry out a numeric simulation for a problem in so many dimensions. And the method by the moment measured by Grad that is the classical paper in 1949, and it's trying to reduce the computational cost for the Boltzmann equation. And the essential idea is try to use only a few degree of freedom to represent the distribution function at one point, and it is using this expansion, and we expand the distribution function in such a formula, and this h and is the derivative of this exponential term, and this is the first one of this is the weight of the Hermite polynomial, and then by this expansion, and we bring this expansion back to the Boltzmann equation, and then the ordinary differential equation can be obtained for all these coefficients, and it is looking like this one. And yeah, it's quite complex. Actually, this is an infinite ordinary differential system, and to carry out a numeric simulation or do some analysis, and we should cut off this expansion at a certain expansion order m, and so this is the very classical Gauss 13 moment equation, and this is the rho is the density, and Vr is the velocity, and theta is the dimensionless temperature, and some other quantities such as this sigma ij is the stress tensor, and looking like this one, but there are only 13 equations in this formulation, and basically this system is a hyperbolic system with a damping term. This damping term is coming from the correlation term, and this game can be played further, and to get such as the Gauss 26 moment equations, and accept the equations in the last slide, and we need to add some other equations as here, but it is extremely long that I can't copy it from the reference here. In this paper, and there are very excellent exhibition of very involving calculation and asymptotic analysis, but unfortunately, and this moment method is not so success. Yes, since the most criticized point of this to using this system to carry out to using this system is that there will be subshocks in the profile of a shock. This phenomenon was discovered in about 1965, but actually in another paper by Grant himself in 1952, he himself already found that there will be subshocks in the inner shock, but physically we know there should be no such structures. So this we need the so-called regularization for this system, and but the problem is that can we carry out such kind of regularization and to the equations to more than 26 moments, and actually it is quite difficult to derive such kind of equations, and the momentum equation itself is very hard to be derived, and at the same time, if we want to carry out the normalization, and the coding is a nightmare, and the last thing is that it's difficult to make the regularization to get the physical solution. There will always be the subshocks in the profile of a shock. So, in fact, though it is beautiful in mathematics to use the momentum system, there are no practical applications until now. And then the other thing I should mention is that the so-called Chapman-Enskog expansion, and this expansion is trying to make a expansion of the distribution for around the local Maxwellian, and this epsilon is the Lewis number, is the collision rate, and so historically, and this expansion is very successful in derives Navier-Stokes equation, and with this expansion to the first order, we can get the Navier-Stokes equation, and then the second order and the third order expansion, and will give us Berlet equation and the super Berlet equations. This is another way to give another way to relate to the Boltzmann equation and the macroscopic fluid equations. But actually, this Chapman-Enskog expansion is criticized by that those high order expansion is unstable. Yes. So to calculate this Chapman-Enskog expansion, we need some regularization too, and these are some works and recently, but in fact the techniques and in this paper are very special to such as the Berlet equation, and it is very hard to expand to very high order expansions, and much long time than those regularization, and in fact in 1970s, and there is a very negative comment to those high order method, and it is claimed that these high order equations have never achieved a lot of success. Yeah, another thing we should mention about the similar in the similar topic is that the DSMC, that is the direct simulation using Monte Carlo method, and it is even throw away the Boltzmann equation and directly to carry out numeric simulation for molecules. And it takes every molecule as a ball and try to calculate the interaction of every two interaction of loose balls. And it in 1960s, this method is not so advocated because due to the stochastic laws, and at that time we can only carry out numeric simulation for about 5,000 molecules, and so stochastic laws it is even bigger than the solution itself. But with the very fast improvement in our computer, and now this method can give quite good agreement to the physics data. So this method is now very popular, but it is criticized in certain aspects. And recently there are some other works, and it's trying to bring back some new hope to this moment method. Is trying to use the compilation of the grad method and Chapman-Anscombe expansion, and this system is called the regularized certain moment system, and it is the merit of this system is listed as follows, and there are a lot of other things, and it can be rationally derived from Boltzmann equation, and it can contain the Berlet and sub-Berlet in Chapman-Anscombe expansion, and it's linear stable, and get smooth shock structure for Mach number less than 3, and for the linear case, and the H term is valid. The basic idea to give this system is to carry out the graph moment expansion at certain moments, and then we assume that the remaining part, it is a lot direct cutoff as a graph. It is assumed that the remaining part have a faster time scale than the 30-moment solution, and then carry out a symptotic expansion, and we can get a regularization term. But actually, yeah, 13 is not a magical number. Yeah, so how many moments do we need in a practical problem? And but the authors of the R13 system, and they said that 13 moments is the minimum, because you should have at least 13 moments, and we can catch the jump and slip, and the Newton-near and the non-near back effects. This is a very common thing in such as microflow simulation. And but for Mach number greater than 3, should we need more moments? Generally, we believe that with more number of moments, and we can resolve the solution for bigger Mach number. But it's there. The number of the moments should the more the merrier. Yeah. So the authors, and they are trying to derive the system for such as 20 moments and 26 moments to get the regularization, and they call this method as NRxx, and that is means role as the system for a lot of moments. But even such kind of system can be derived. The problem is who will use the high-order moment system to carry out numeric simulation. Yeah, there are so many nonlinear terms in the convection, and it is extremely difficult to implement the code. Yeah, so afterward we naturally recall that the object to derive loss momentum system is trying to reduce the computational cost of the original Boltzmann equation. Yeah, so for a solver with either efficiency, and what should we do? And actually we want to use the moments as many as enough to resolve the flow, but not more than that. Yeah, so if we want to have such kind of ideal flow, ideal solver, and only if it can be developed, we will use a class of different models at different locations in the domain, depending on the magnitude of the Raphael effects locally, and such as the exterior flow field around the airplane, and the far field should be directly simulated using the Euler equation, and there are some transition part, and we will use Navier-Stokes Fourier system, and very close to the surface of the aircraft, and we need to use some system with higher order expansions, and then to approach such kind of case, and we at least will lead the following items. And the first thing is that we lead a class of different models, and these models can be used in practical computations. And the other thing is that these different models should be coupled, and we need to have the method to couple these different models. And the last thing, and we lead the strategy to decide which model is suitable locally. And so the method we developed, and that is called the numeric regularized NRxx method, and we think we are now on the way to this object. And now what we can do is list the following, and we can have a class of models, and then these models can be used in practical computations. And then the last thing is that the coupling of different models is seamless. Yeah, our approach is trying to skip the step to derive the momentum equation. We directly use the grad expansion, and then numerically implement the whole procedure to derive the momentum system and the regularization. Yeah, so let's try to play the game, and to carry out numeric simulation. And we are very far away behind the lines of the PDE, and we are not considering the classical Boltzmann yet, and we regress from the Boltzmann equation to the BGK model. And the collision term is using this most simplified formation, and it is a damping to the local Maxwellian, and then the Maxwellian is in this formulation. The parameters in the Maxwellian, that is the density and velocity, and the dimension is temperature. And so And let's expand the distribution function into this Hermit using the Hermit polynomials as basis function. The only thing we do different from the grad that we introduce a scaling factor here, and all the other things are the same. And then we, with this expansion and the starting part of the moments, that is the f0 is density, and then since we are expand at the mean velocity, so this moment 0, and the expansion is at is scaled by the dimensionless temperature, and then we have this relation. And the macroscopic equation as the Euler equation can be obtained similarly. And so then we cut off this expansion to a finite number m, and then we use this cut-off expansion to correct the numeric simulation, and now the correlation term is very simple, and since that Maxwellian is the first term of the expansion, and now the correlation term is looking like this one. Yeah, and this expansion actually it can be it can be carried at other locations other than the mean velocity and the z theta, and we can have a very simple relations between this rho and the expansion to other locations such as u prime. And now we give the mesh and we triangulate the domain, and now we are using a Cartesian mesh and for simplicity, and then use the standard Fallot volume discretization and looking like this one, and we use the standard two-step method. The first step is to adapt the convection, and then the other thing is to add the effect of the collision term. And in the convective step, and we need the so-called numeric flux, and this numeric flux is chosen to be the HL scheme. And in this HL scheme, and the problem is that the expansion on the boundary of two cells, they expand at different parameters, and it is expand on its own mean velocity and dimensionless temperature, and so we need some techniques to add up the terms looking like this one, and in the expression, the first thing is when we try to calculate this QCG times the expansion, and the other thing is that we need to approximate the maximum singular speed. And if all of things can be calculated smoothly, and then this scheme will be it will be approximation of the grad procedure. Yeah, so the first thing is that we calculate this QC times this expansion, and it's very simple. We can directly use the recursive relation of the Hermit polynomials and to give a very sparse expression, and then the other thing simple is the production step, and it's very simple that is the ordinary differential equation, and we can directly get the NRxx expression looking like this one. And the complex one is try to add up two functions in different space. And that is actually there are two polynomials. One is the polynomial of x. The other is the polynomial of x plus 1. And numerically, we only have loss coefficients of the polynomials. And then how can we add up these two things efficiently? Yeah, we don't want to. We want to keep up the numerical efficiency to the level that is the of the number of the moments. And the other thing is try to estimate the characteristic velocity. And so to make the first thing, and we are trying to project a function in this expansion and to a function in this expansion. And the basic idea here and is we are since these two expression as two expansion are expanded depending on the local parameters, so we introduce a linear homotopy to for homotopy from u1 theta 1 to u2 theta 2, and with this linear homotopy, and then we can obtain a with this linear homotopy, we require that the derivative of f depended on the parameter, and the derivative should be 0, and then we achieve the projection. And so for finite number of moments, and it tends to be a ordinary differential system, and the formation of this ordinary differential system is very special, and we have only two terms here, and this coefficient on the right hand side and have a smaller subscript than the left one. So for this system, if we cut at any m, and this system itself is still closed, and so we can make use of this thing and to do the homotopy for m to be finite. And at last we need to solving such a system, and since we are introducing net additional scaling number in the ground expansion, we can find that in fact this coefficient matrix A tau, it is an uptriangular matrix, and the diagonals are vanished. So in fact, this system, it is a lot of ordinary differential equations, and it can be, the solution can be obtained by recursive integration, but the direct integration will lead to the number of operations on this scaling, and in fact we solve it by using an open-step longitudinal numerical integration. And since the diagonal part of this matrix are all zeros, so this longitudinal integration is unconditionally stable. So so this makes the projection procedure, and it have cost only on this level. Yeah, so then with this projection, and we can apply the projection operator, and then bring it back to the calculation of the convection, and it can be verified that all the microscopic quantities will be conservative, and using this projection. And then the other thing is that the characteristic speed, and it is required in the numerical flux. And for this thing, we at last actually we need to calculate the derivative of the numeric flux to the derivative of this expression to f1. Yeah, so at last we turned it into the calculation of the single speed of this Riemann problem by some derivation. And in this formation, and the numeric flux, the flux function is looking like this one, and it is a Cauchy, and then there is a projection pi f, and with this operators here, and this is its inverse. Now, with those things, we need only to estimate the single speed of this operator, and that is times by Cauchy and the projection pi f. Yeah, at last we can prove that this part, yeah, its eigenvalues are in fact the zeros of the Hermite polynomial, and so at last we can give an approximation of the singular speed. Yeah, so yeah, until now, actually we have numerically implemented the Gauss procedure, but that is not the end, and the regularization is always needed. Otherwise, we will have these long physical structures in the shock profile. And at first, we are trying to mimic the method used to R13 system, and we use the Chapman-Enskog expansion around the numeric solution we can already have in hand. And doing this thing, we can derive a regularization term looking like this one, and it is a diffusive term for the distribution function. But after some numeric simulation, and though we can repeat all those numeric examples in the literatures, but we found that for Mach number bigger than 3, and there still will be some blow-up behavior to use this regularization. So now we are let me skip some technical details. Yeah, so we are now trying to improve this regularization using the so-called Maxwellian iteration, and this procedure is looking like this one, and we substitute the ground expansion back to the BGK equation, and then match the coefficients of the basis function, and we get this equation. And the only thing different is that we move this tau from the right hand side to the left hand side, and then we can take this equation as an iterative scheme, and with the initial value to be the Maxwellian, and we use the Maxwellian as the initial value, and we substitute it here, and then get f1, and then bring back it here to get f2. That is the so-called Maxwellian iteration. And actually, this G alpha in this formula, it is linear to all those parameters, and actually it can be written in this formation. And there are only all the moments. Yeah, for this f alpha, there are only all the coefficients with alpha is as small as alpha minus 1, and the greatest one is this alpha plus 1. So using this relation, and we can carry out a so-called the order of magnitude analysis for all the coefficients, and then the first step of the iteration, and it will give us this things, and that is the coming from the standard Euler equations, and then we substitute the obtained coefficients and back to the iterative scheme, and to get the second to give the second step of the iteration, and then it is looking like this one, and at last we can find such things if this alpha is bigger than 4, all those coefficients will larger than our tau square, and for this alpha bigger than 7, and another step of the Maxwellian iteration will give us that the coefficients for alpha equal to 5, 6, and 7. It should be of the order tau cubic. Yeah, so generally we can have these things for all those coefficients, and the order of the magnitude is in fact in nature scaling, and that is alpha over 3, and we take the scaling of to take the scaling of this quantity, and that is the integral only bigger than this number. So with the information of the magnitude of all those coefficients, and then we can try to remove all the high order terms in the momentum system, and it can be reduced to this formation with some high order terms, and then we can substitute the Navier-Stokes Fourier equation back to this part, and at last it is it will give tell us that some of the terms, and in this expression they are still of the high order, since the heat flux and the stress tensor are of order tau, and then finally we threw those high order terms away, and at last we can achieve this expression, and then we use this expression for all terms for alpha equal to m plus 1. Yeah, since for m alpha equal to m plus 1, we cannot represent these expressions in our numerical simulation, and so we use we use this expression. All the terms here are actually the coming from the coefficients lower than order m, and to be approximation to the high order part. Yeah, so, and to carry out a numerical simulation, to use such kind of term to be the regularization term is still too complex. So we try to simplify this part, and for a simple implementation, and this procedure is called the linearization. And we linearize this regularization term in the neighborhood of a velocity-free Maxwellian, and we suppose that the radius of the neighborhood is epsilon, and we substitute this epsilon to all the variables, and then with some calculation, and we threw away all those terms of high order in epsilon, and then we can get this expression, and we intentionally keep one high order terms here for the convenience of restoration of the variables, and it at last to give us this term as the regularization. And so yeah, if we use this term as the regularization, and at last we add a diffusive term looking next this one to the momentum equation. Yeah, now this term is clearly it's diffusive. It's not only the diffusive on the distribution function itself. It is the distribution to the moment. Yeah, so this can make the behavior of the graph system much more stable. And one thing is that the linearization is carried out at the velocity from free Maxwellian. And in fact, in the NRxx simulation, we cannot have the much difference between the linearized regularization term and the net that very complex one before the linearization, since actually the linearization can be carried out with all the moments with order less than m minus 4, and then the difference actually is the linearization actually can carried out very close to the actual solution. Yeah, so at last we come back to the algorithm, and we start from m equal to 0 and the initial guess, and we determine the time step length based on the CFL condition, and then apply the convection step, and to get the and then we add the regularization part of the numeric flux, and then apply the production step. It's a very standard procedure. The other thing is that is the computational cost and the boundary conditions, and the computational cost is in this scaling, and it is much more reduced. And the boundary conditions is not available until then, since the boundary condition of the graph system is extremely complex problems. Yeah, so the last numerical result, that's short tube test, and this is only interesting for referee, and since this is try to show this method is correct, and it can produce correct solutions to compare with the no things in the reference. Yeah, so this one for the Newton number equal to 0.01. This is coming from the reference, and using the R13 system, and it can get about very close to the correct solutions, but with the Newton number to be much larger, and then the R13 system cannot give the correct numeric solution, and so yeah, we can carry out the computation for a lot of different numbers of moments, and then at last there is a convergence with the increasing of the number of moments, but for much larger Newton number, the convergence is much more slow. As you can see that for Newton number to be 1/2, and until there we have 84 equations for every point, and the convergence is not clear yet. But if we increase these things, and with m equal to 7, 8, and up to mx to 12, and we have 455 moment equations at every point, and then we get quite satisfied convergence to the BGK solution. And the other thing is that the shock structure and at high Mach number, and we increase in the Mach number from 2, 4, and up to 6, 8, and we still can get smooth shock structure using the Liu regularization method. Yeah, actually, all those things cannot be obtained using the tradition and the traditional numeric techniques and the computational time. And then let me show something different, and that is we now, with the improvement of the efficiency, now we can carry out numeric simulation, yeah, for x to be two-dimensional case, and there is a really three-dimensional velocity, and totally, and the problem is in 6 dimension, and yeah, since they are low analytical solution, and we can only check the numeric convergence of the numeric convergence looking like this one, and with the numeric convergence, it is believed that the method should be correct. Yeah, so we are working on some other things related, because there are too many things to do. Such as the different kind of boundary conditions, and for polyatom gas, and we are trying to fix the Planck number using the Sharkov model, and for the numeric techniques, and the method should be extended for unstructured grid and piecewise linear reconstruction, and the time-step reenlargement to implement the numerical accuracy order, and at last we need a parallel computation. And so let me stop here. Thank you very much.
Questions?
I have one question about the difference between grad usual expansion and your expansion.
Yeah. Yes. That's the. Yeah. Actually, the difference is only this scaling factor. Yeah, we use this scaling factor, and then in the projection procedure, and the diagonal part of that matrix will be vanished. Yeah, otherwise we can't have such kind of algorithm.
Can you show, for example, if you pick some m, the number of moments do you get a hyperbolic system?
Fix some m.
We have this class of models. You have a class model. Can you show some hyperbolicity of this?
Yeah, for we can. There are no problem.
Or there's no hyperbolicity because it's kind of a superimpose some of the grad solution.
Yes, I think
Well, that's one of the main problems with grad ability. It's an elliptic region. So I'm wondering.
Yes.
Do you get rid of the elliptic region, or no?
Yeah, currently we can only carry out the stability analysis for the linear line state.
It's a linear stable.
Yeah, it's a linear stable, but actually for m equal to 6 and the linear stable stability ion lines will give the worst result, and the stable region is about the minimum, but I don't know why.
about if you linearize, it's a hyperbolic.
Yeah, sure. Yeah, for linearized system, it's hyperbolic, and
But for nonlinear, you don't know.
yes.
Okay, so there are no more questions. Let's thank the speaker again.